Okay, so we are going towards the grand finale from the last two chapters. That is on the data modeling and also evaluation using the machine learning, and as well as how do we do the interpretation. So these are the two. I think we have around like 12 sessions more until your finals. So we'll try to cover all those aspects as soon as possible. Okay, so today going to be a bit more on theoretical side. So previously we have actually done this EDA, which is known as exploratory data analysis, and as a result of it is where all of you have done your project 1, and which is due tonight, right, for you to actually submit. So the whole idea is to get familiar with the structure of data set and also to try to do feature extractions, right? You actually want to see which one of those features are actually directly affecting the other variables and things like that. And do you remember the various methods that were actually presented? Do you remember what are the three visualizations? Very quickly. What are the three types of visualization that that we use for exploratory data analysis? No, that is the chart. Yes, univariate. I did mention that it's important, right? So by right, if you have captured whatever I've said, if you didn't capture, then you're lost lah. There's nothing much that I can do if you're not capturing. We have been repeating that so many times. By now, I've already shared some few things that will enable you to answer almost one question. And today we'll see two more points. But if you're not capturing and things like that, well, how much that I can do. So yes, that's very, very important for you to actually know those univariate, bivariate, and so multivariate, and how it actually assists you in trying to understand about the data. And with that, you apply certain preprocessing techniques whereby you try to replace with null or empty variables and things like that. Or if you think it's just a small in number, you can actually remove it. But again, remember, you have to look at your data set. If your data set is too small, you should try your level best. The removing from the data set should be your last option. Nevertheless, you can still try to run it with the model and see how is the result with and without. Are you getting better results or are you getting worse? So it's a whole iterative process, right? You have to go through the whole cycle. It's not one time you run, then you finish. So after you do the modeling, after you get the evaluation, you get the results, then you may have to revisit back on the data. You may have removed. What if now if I try to remove all those null, does it give a better? So it's like a reiterative cycle. So then, of course, once we have explored the important features, then we are moving on to the next one, which is now we need to choose the suitable machine learning algorithm to model the data. So once you have modeled a particular data, let's say you have the same data. Future instances means you have the same data, so you can feed it into the model to predict the output, because you already have the model, right? Like for example, you have the very, very simplest model y equals to mx plus c, right? If you plug in the y value, or if you plug in the x value, let's say you want to predict, this is not actually prediction, right? But more or less that's how it actually works. You want to know what's the value of y, and you have the value of the m, which is a slope, right? It could be negative or positive slope, and you have the x value. Then if you have the intersect, include, otherwise you don't have. If you plug in, could you get the value of y? Yes, you can, right? You can, because the model is such, y equals to mx. The y equals to mx plus c is the model. So when you feed in what other values, you can get back y, right? So similarly, that's the simplest concept. Similarly, when you actually train a particular model using historic or previous data, and the same format of data, if you after you train the data, you have a model, then you plug the new data into the model, you should be able to predict the outcome as well. So that's the whole idea of data modeling and also evaluation. So of course here, one of the main important things of machine learning is, of course, we are doing programming, right? We are using Python in these instances. And the whole idea is to optimize the performance criterion by using examples or training data. So example means what? Example means row. That's what the terminology is used. Examples. Let's say if they have 100 examples means what? They have 100 rows in your data. But you need to take note that not all tasks require machine learning. Now, for example, like if you want to calculate the payroll employee of a company, do you need to use machine learning algorithms? No, you don't have to. Payroll is simply based on the years of experience, their position grade, and accordingly the number of years of services. Accordingly, you just need a simple mathematical formula to calculate what is the percentage of EPF and things like that, right? It's very, very simple. You don't need machine learning to calculate how much salary you need to pay. So where do then machine learning actually comes? So machine learning is especially required where human skills are not available, or humans are not able to explain their skills such as face and speech recognition, or when it actually comes with a complex calculation, or you have a huge data. You have a huge data. Do you think as humans you can go through the data and try to find some similarities and things like that? It might be difficult. So you have machine learning for you to actually do that. And sometimes learning also is actually required whenever the problem is a time dependent problem and also based on the available data. So it's a very, very dynamic problem. For humans to actually try to come up to make the prediction is very, very difficult, right? Like if I ask you how would the weather be this evening, would you be able to guess? Maybe some of you have the ability to look at the sky and you see the blue, the clouds, and say, yeah, most likely can rain. But you know, given you the fact that okay, every day is raining, for my experience, every day is raining in the evening. Based on that, would you be able to say that it's going to rain also this evening? With a shot, but it may not be accurate at all, right? But if you have the historical data of this year, the previous year, and the previous years, and also the current weather data, then of course the machine learning, learns about all these different attributes of various parameters, and it's able to take some decision prediction with certain level of accuracy, of course. So for example, like you have the routing algorithms may require the previous data to perform better routing. Of course, here is mentioned about net computer network, but if you look at your Waze, for example, how do you actually do the rerouting and things like that? You use this AI at the background to recalculate, to make sure that you spend less on toll and also reach your destination the minimal time. So whenever it calculates, its objective is to make sure that you reach your destination with a minimal time. If suddenly, based on time, there's traffic built up in a particular path, what it will do? It will reroute you back, right? If there's a possible route for you to take, it will reroute back. Now, for us humans, will we be able to do that? No, we can't. Of course, it has a whole infrastructure in the background where it actually captures data in various routes. Then it calculates and finds out that okay, if you want to go to that particular location B, The current one is the traffic is building up. So now you can try to reroute and go this particular path, then you'll reach earlier. So those kind of complexities is where machine learning and algorithms all comes in. So there are several real world problems, like for example, if you look at the customer relationship management in retail business, fraud detection in financial transactions, robotics and control in manufacturing industry, diagnosis in the field of medicine, spam detection and filtering in communications, search engines in web mining. These are all the various applications of machine learning or AI at the background. Even a simple web search, there is a search engine optimization, CEO. That's not SEO, search engine optimization. So whenever you want to actually search for something, you'll see the certain page that will actually come up to the top of the list, right? So it uses all these various types of AI techniques to make sure that whatever that you search, it gives the most relevant search. And if you are a web developer, then you want to optimize the content of your web in such a way that it always will try to return. So you need to understand about the search engine optimization. So if you implement it in your website, so anyone says something about Malaysia, yours will come first, or whatever niche area that you want that you're working on for your website, for example. So basically every single thing that you are seeing or you're using, it's all using AI. It's capturing data. So like they say, whenever the product is free, you are actually the product. You're actually providing free data. You are the data provider. So nothing comes free. No such thing as free lunch. So everything that you're providing, you're using Facebook for free, right? Using TikTok for free. Everything you're using for free. But someone else is making money. Not you. Of course, some TikTokers or some YouTubers, yes, you do make money out of it. But other than that, they're using all your various data, use the platform to actually do marketing, to understand what the people's needs are. So all these things are using machine learning. Now coming back to the machine learning terminologies, there are basically, actually there are more than two major categories, but we just focus on these two major categories. So you need to know this as a data. Class okay, sorry about that. So as a data science students, you should know these two terminologies: supervised and unsupervised learning. Of course, there are also such things as reinforced learning and things like that, but that is not covered in the scope of our syllabus. But these are the two major categories. So what is meant by supervised learning and unsupervised? So supervised learning is a type of machine learning where you use the data having label outputs. Meaning to say that supervised means you want to predict something. You have a label that you want to predict. That is supervised learning. So for example, if you see under the USA housing dataset that we have actually used, there is an attribute known as the prices of the house, right? So if you are going to use that USA housing dataset to predict the price of the house, that means you want to do some prediction, right? You want to predict based on the other attributes. Now we have done before, we actually did the multivariate chart, right? We actually did the metrics, and we found out there are few attributes which are very strongly correlated with the price of the house. I can't remember the exact attributes, but I think it's the area, population or something. There were 2 or 3 that were very highly correlated with the prices of the houses. So of course that data set already have the price of the houses, right? The data set is complete. It already has the price of the house. Let me see. So this is the USA housing data set, but you can see the price is already there, right? All the prices are already there. Of course, this is a complete data set, right? And you are going to use this data set to actually train your model. And when you have a new data which has all this average area, all these attributes, a new data, when you plug in into the model, you'll be able to predict on the price. Are you all able to follow? So again, we also check the iris data set, right? There are 3 distinct species. I think there is iris virginica, versicolor, and also there are 3 species. But remember that these 3 species actually have different sepal and also the petal width, right, and length. So let's say if we have the data of the petal width and also the petal length, if you provide to the model for it to predict what is the species type. So it will be able to predict what is the species. So in this case, where you want to actually make it a prediction, of course, if you notice one thing, what is the difference between the USA dataset prediction and also the IRIS dataset prediction? Anyone can identify the difference? In both cases, we want to predict something. So it is definitely a supervised learning. You want to predict. But what is the difference between these two? Can you identify? Sorry? One is? Sorry, maybe you can remove. I can't hear. Oh, then? It is supervised. Both are supervised. Because both we want to actually make a prediction, right? One is we want to predict the house, the price of the house. The second, we want to predict the species. But what is the difference between these two? Prediction label. So when the attribute that we want to predict, we usually call it as label. Label. Sorry, you were saying something? Okay. Okay, coming closer, what is the nature of the label attribute in USA housing and also in IRIS? The data type. We have learned about data types before, right? This is a continuous or categorical? The numeric value, right? The price is a continuous value. How about the species? It's categorical, right? It's only have 3 category species. So both are labels, but they have different nature in terms of label prediction. So when we are using labels, so labels mean what? You want to predict something from the data set. You have a lot of attributes. You want to predict something. So whenever you want to predict, that is supervised learning. So make sure you are very clear on this. So when we use the label means the attribute that you want to predict. So that is automatically supervised learning. So under supervised learning algorithm, there are 2 main. One is classification, another one is regression. So the USA housing dataset falls under classification or regression? Regression. It's a numeric value, it goes regression. And the IRIS dataset, you classify them based on the types, right? So if the output have a continuous range of values, it's a regression. Oh yeah, the answer is down here. The continuous range is a regression. If it has a discrete value, it's a classification problem. Are you all okay? So supervised and unsupervised. Supervised, you want to make prediction. And under supervised, there are two categories, which is classification and regression. All okay? Now, what is unsupervised? Now, under unsupervised is that you are not interested in predicting. You are actually interested to understand what this data, what is the insight from this data? What is the story that this data has to mention? So this is, you are not trying to predict something. So the goal is actually to identify meaningful patterns in the data. So this is actually known as unlabeled data set. And what it will do, it will try to categorize the data and try to infer some rules in trying to understand what kind of pattern that we can actually infer from this data. Like for example, as one project that I was doing on COVID, using, I'm not so sure if any one of you have participated in the survey where you're required to submit your mobility data and you get some token of money. I think the next round will be coming soon. So if you want to participate, you can participate also. So basically you are giving away your mobility data, but don't worry, whenever you're giving your Google mobility data, there's no personal info. It's purely on your latitude and longitudes, and also the probability of how you are moving from one place to another place. So students submit all their mobility data. Of course, they get money in their e-wallet. So the next one is coming up, so I'll keep you informed if the one ready. So having all this latitude and longitudes, all this data, lats and longitude data, is there anything I can predict? Latitude and longitude. I only have the lat and also the longitude data. So there's nothing I can actually predict, right? I cannot be predicting the longitude data. I cannot be predicting the latitude data. But what I would want to see is when I plot those, let me see if I have it here or not. Yeah, I have it here. So this one is an example. Okay. This is the plotting of all the latitude and longitude data. I'm not predicting anything. What is there to predict? The prediction comes later point lah. But I'm using one particular algorithm. Let me just try to focus it. Yeah. Can you identify where is Uniden? Here. Now, I've plotted something. What can you tell? This is Uniden. What can you tell from here? Do you know what is this? Chendi. This is a sports arena, right? This is Ilmu student. Ilmu. This is your mosque. Do you know what's here? Up 10. Do you know what is this? Do you know what is this? Food court. This is Ilmu. Do you see any patterns here? Of course, what is this? The centrum. Do you see any patterns here? Now from here I can see where students are the most congested, right? Am I making a prediction? No. So this is an example of unsupervised learning. You are trying to look for some patterns. So here I can see that, okay, mosque, student subject. Of course, later if you do in terms of, this is known as density-based clustering. Earlier is classification. Huh? Under supervised learning is known as regression and classification. This is known as clustering. You try to cluster your data and try to look for some points where you can see some patterns. So this is actually for a COVID study pattern. We want to try to understand students' mobility. So from here, of course, we will be doing on the next location prediction. So when I know where students are, okay, now is pauser time. But if not during pauser time, of course, now during pauser time, you will see a different types of trending. Where do you think there'll be most people? Most people will be here. Do you know what's here? Bazaar. And you'll see that during the before your breakfast time, right? And you will also see more students at COE here during, because a lot of people will go into the bazaar. And what's the time period? It's a particular time, right? So we can actually do a time base to see where students will be at a particular location. So based on that, let's say if there's another epidemic, let's hope not. By using this model that we are working on, this particular project, we'll be able to know where students' mobilities are. And with that, we can try to place some restrictions. Okay, there's too many students here in COE, so we have to have a hybrid to limit things like that. You got the point? I mean, the point I'm trying to say here is we are not predicting anything. We are looking at patterns. Got it? So that's what we're actually trying to do. So here, this is another example. If you have the plant leaves without knowing the names of the plants, we do not know the output labels. So this looks something similar to like the iris dataset, right? Iris dataset has all these various plants, leaves, length and also width, but it comes with the output label, correct? And you can use whatever the other attributes to predict what species is that. Now let's say we don't have that species attribute. What can you do? You can still apply clustering, and it will try to cluster based on the length of the sepal. So when you actually plot it, you'll be able to see certain groupings in the plot. You're not predicting anything. You're not predicting the species. But when just by having the sepal width and length, when you plot it in terms of the width and length, you will find there are categories. So that will tell you that, hey, oh, there is 3 species or 4 species. But you're not predicting anything. You're just trying to find out, right? So it will able to differentiate between the different types of leaves. Because each species have their own characteristics, right? So you'll see that the data points will be certain groups. So under the unsupervised learning, there are 2 main tasks which is known as clustering and also dimensionality reduction. Now this dimensionality reduction is also an important point. Remember that most of the final questions will be coming from this chapter onwards. And whenever I say certain things are important, so make sure that you actually put in a lot of focus. We will cover this point on the dimensionality reduction. So dimensionality reduction is a very, very useful feature, especially when you have a huge data and it actually takes up a lot of computing resources. How can we actually reduce the dimension? So dimension reduction means in terms of the columns, not in terms of rows. So you have a lot of columns. How can you actually try to reduce that columns? You're not reducing the rows. So we will see that. So under the clustering, we will try to group the data based on input features. So whatever input, the length of the sepal width or things like that, we'll try to group them. Whereas in the dimensionality reduction, we'll try to reduce the dimension of the data to only come up with the salient features. Salient features means important features. So these are the two things under the unsupervised. So here are some of the terminologies that we need to actually learn is training and also test data. So when we say a model, we are saying we want to develop a model, right? So what is a model? It's nothing but a mathematical description or a formula to describe a data set. So later I'll show you one image. And when we say it's a linear model, how can the actually model represent a particular data set? So to model a data set, usually we will divide your data set into training set and also test set. This is part of the methodology. So let's say you have a data set of 100 rows, 100 examples. Now when you want to build the machine learning model, you need to split your data set into training set and also test set. So what is the the training set? So let's say, for example, out of 100 rows, now the ideal one is you take the 70% of your data as your training data set, training set. Where out of the 70 data rows, you take it out and you identify that as training. So you use this data to train your model. And then, this remaining untouched 30. Now, after you use the training set, you get the mathematical modeling. Then you take the balance 30, you try to plug it in to see whether is it able to predict correctly or is it able to cluster correctly. So the training is used to develop the model. The former is used to build the machine learning model, while the latter, the test set, is to validate the built model, validation. So data points in the training sets are omitted from the test sets and vice versa, which means they don't use the same data set in both. Training set means it's just training set, test set is test set. Are you all okay? Any question up to this point? So in machine learning, we will try to generalize the prediction capabilities of the built model. What do you mean by generalize? So what it means by generalize the prediction capability means whenever you have the data set, the training data set should be representative of the entire sample. It shouldn't be just a specific sample only. It should be a general model that whatever types of data that you actually provide in, you should be able to predict. So to test the generalization power of the model, we select the data from the data set that is not used in the creation of the model. So you can see here, this is your entire data set. Out of the entire data set, let's say you take around like 70%. This one looks more like 80%. 80% of the data for training. And the balance left out is the testing data. So you use this testing data to test and see. What do you think if we reverse this portion? What will happen? If the training is only 20% and testing is 80%, what will happen to the generalization power of the model? What do you think? It may not be accurate because you are only using a small data set to train the model, right? Whereas there's a huge data set here which is not used. So when you use it for testing, you may find that the power of the model is not generalized. The model is more biased towards only this small sample, right? Do you understand that? If you're just using a small data set to train the model will be accustomed to this small data only. There could be some other variations of data in the larger data, but you have not trained the model with that. So the the power of the model, it is the generalization power is not so strong because it's just you are using just a small data set. The knowledge it's very limited. But if you train with a larger data set and you test it with a small percentage, the generalization power becomes better. Got it? Able to understand? So the portions is usually, but this is not the set rule is usually like 70-30. 70% we try to use for the training set and 30% for the test set. However, this division depends on the type of task that you have at hand and also the data set. Now again here, remember I mentioned that this whole process is a reiteration. Maybe now you choose 70-30, then you train the model, then you validate, you get accuracy. Then you try to go back. What if I train with 80%? Then 20. What if I do 60%? Then you may ask, sir, why don't we just train 100% or 90%? There is another term that is known as overfitting the model or underfitting. We will come to that term in our next class. We don't want to overtrain the data such that it overfits or underfitting. We will see what those terms are. So generally, if we choose like a certain percentage, 70 and 30, it should be fine. But again, you can retest back. How about 60-40? What happened to the accuracy? What about 80-20? What happens if I do 90-10? 50-50? Yeah, you can actually explore. Because every data set is not going to give you the same accuracy. It's all different. You just mentioned 50-50, here's 50. So when you train the data from 50, definitely is going to be different from your training from 70-30. But as a rule of thumb in machine learning, the bigger the data set to train, the better the trained model and its generalization power. Generally, if you later on when we actually do the machine learning, you try to play around with the percentage and see, then you'll be able to realize. Now this is very important, cross-validation. Now generally we actually split our data, so you need to know what cross-validation is and what also the importance of cross-validation. So generally we split our data set into training and also test data sets, right? So we keep aside the test set, that means whatever 30% you keep aside, take the 70% and you train the model and you use the remaining part of the training set to validate. So this reserved portion of the training set is known as the validation data set. You use it to validate. So these are some of the terms. Training and test data set. Training is you use to develop the model. The test data set you use as a validation. It's also known as the validation set. Yeah. No. When you're using the cross validation, is the approach of how you use the training and also the testing set. So if the model is iteratively trained and validated on different sets generated randomly from the training set, and when you do this iteratively, this is known as cross validation. Still you have two only. So of course we will look into this much more deeper and when actually doing the machine learning models. So sometimes when you have this one, for those who didn't come for class, sorry lah, because I'm going to draw on the board, so I can't capture everything on the screen, right? I'm not so sure whether it's on books or not. So there are various methods actually. So let's say if you have your data set, right? You have your entire data sets. So let's say we have 100 examples, for example. You need to split this into training, data set, and also the test or validation, right? Now usually this one will be like 70% and this one will be 30%, right? Now there are various cross validation. So now if let's say we have, this is the 100 rows, so imagine you have 100 examples. Now if for training, if I just take the first 70 only and train and leave the balance 30, I'm just taking the first 70, that is may not be representative of the entire data set. Maybe the balance 30, there are some data set with the other variations, right? You might have missed. So when you take this example, this from just the first 70 only as your training data set, is this 70 is representative of the entire data set? No, it's not. So that's why when you actually want to use the cross validation approach, it will actually take, yes, 70%, but it'll take maybe one here, one here, one here, one here, one here. Randomly it will take. So that the training data is representative. So later we will see on this sampling. In the next class we will see that also. So you will see that the cross validation is a very, very important aspect, because if you just choose the first 70 or the first 50, it is not representative of the entire data set. So when you iteratively take data points from randomly from different various locations, but of course the percentage is 70. But now in your entire data set, you're taking everywhere. Now this is 100, right? Let's say if you have a huge data set and it has a very dynamic attributes and rows, you want to make sure that whatever that you are selecting to train the model, it has to be representing the entire data set, right? It shouldn't be just focused on a particular portion only. So that's why cross validation is actually very, very important. And whenever you do this cross validation, it actually will help the model not to be overfitted or underfit.